may take some time for the projector to warm up. I guess my computer is connected.
It's a black hole.
It's a black hole. There we go.
It's warming up. Yeah, that's my desktop background. You know, this picture is actually edited by Apple. There is supposed to be a smaller galaxy, but I don't like it, so they edited this picture. Okay, good. Good evening, everyone. I'm Dr. Marie Lau. Can people at the back hear me?
Yes.
Thank you, thank you. I'm a project scientist / lecturer at UC Riverside. This is my first time visiting Orange Coast College, and I already like it here. A lot of buildings are new and well furnished, it's well lit. And this afternoon, I took a walk around the astronomy house at this planetarium, and I really like it here. And I can see there is this vibrant community centered around this planetarium, and I appreciate that. And I also know OCC has a strong astronomy program, so I really want to thank the organizer and the astronomy department for inviting me. It's actually this gentleman at the back, Trevor, who invited me here. And tonight, I will talk about quasars. Quasars are some of the brightest and most mysterious objects in the universe. And we'll start with the basics. What is a quasar? And explaining the quasar phenomenon will require describing supermassive black holes. And then I'll talk about the bigger picture, connecting evolution of galaxies and quasars. And I'll talk about how we study them. We study them using modern telescopes that can peer deep into the universe. And then I'll share some recent research findings from my own work. And I'll end with a look at the future of this field and how you too can get involved. And I put down the logos of the research institutes. Is the cursor showing? It's not okay, so I'll use the laser pointer because, okay, my cursor is here. I use the cursor. So I put down the logos of the different. No, I should not touch it. I should not touch anything. No, I'm not touching it. Maybe we try the traditional method of just unplugging and plugging it back in.
That always works.
Okay. Okay.
Yeah.
Okay. So I put down the logos of the research institutes I've been supported by. UC Riverside is famous for growing oranges. If you ever have a chance to visit, you are allowed to pick the oranges on campus if they're not behind fences. I think we actually have more orange farms in Riverside County than here, Orange County. And I did my PhD in UC Santa Cruz. The mascot is a banana slug and is holding a telescope. And I also use resources of the Keck Observatory. I use resources of the Keck Observatory located in Hawaii. And I also use resources of another observatory, the UCO Lake Observatory. that's located in SF Bay Area. Okay. And I'm funded by the Space Telescope Science Institute. I also want to acknowledge my collaborator, Dr. Serena Peralta, for helping to prepare some of the talk materials. I wonder if I'm straining the cables too much. Can I ask the organizers, does that happen often or is it just tonight?
It happens often. Yeah. Do we want to try to hook up the laptop in the back?
I know, yeah.
Well, now it's back on. If it happens again, then yeah, I will try using the system at the back. Yeah, to set the stage, let's give some context. And let's start with galaxies and how we observe them. These beautiful pictures of the night sky with the Milky Way are taken by this astronomy enthusiast. And the top right picture, this one is taken at Eastern Sierras, and this bottom right picture is taken at Joshua Tree. I only do astrophotography with my cell phone. I don't have the equipment to take pictures like this. And our Milky Way is one of many galaxies. And galaxies can come in many shapes: elliptical, irregular, spiral, barred spiral, etc. The study of quasars belongs to the branch of astronomy called extragalactic astronomy, and sometimes is in cosmology. And just a quick revision, what is light? White light is composed of all the colors of the rainbow. And what our eyes can see is called visible light or optical light. And there is light beyond the colors of the rainbow. Our eyes can't see those colors. Light is electromagnetic radiation. Electromagnetic radiation consists of waves of the electromagnetic field propagating through space, and it carries radiant energy. And the light we observe from galaxies comes from a variety of sources, namely stars, gas, dust, etc. And here we have optical, radio, and infrared images of the same example galaxy. Stars shine most brightly in optical wavelengths, and then cold gas emits mostly at radio wavelengths, and dust emits in the infrared. And we need observations across multiple wavelengths to capture all the components. We need telescopes that can observe at all wavelengths to fully understand a galaxy or any astronomical object. Quasar is an unusual phenomenon that happens at a galaxy center. A quasar is an extremely bright object found at the center of a distant galaxy in the early universe. It's powered by a supermassive black hole at the center of a galaxy. The black hole is actively feeding on the surrounding gas. And as the gas falls in, it heats up and glows, and that creates a quasar so luminous it can outshine all the stars in the entire galaxy. Quasars emit an enormous amount of energy, and they're visible across billions of light years. These two are Hubble Space Telescope images of two different quasar host galaxies, and they are respectively 2 billion light years and 600 million light years away from us. The quasar is a compact region at the center of these active galaxies. And the top picture also shows his jet. This is real, this is not noise. And then the bottom picture reveals more of the galaxy. And I also have a sketch of how a quasar emits light across many parts of the electromagnetic spectrum. So radio, infrared, visible, X-ray, and more. And the electromagnetic spectrum of an active galaxy, meaning hosting a quasar, is compared to that of an inactive galaxy. A quasar emits more radiation than the rest of the galaxy beyond what can be attributed to just stars. Supermassive black holes. They have masses millions to billions of times our sun. A supermassive black hole lies at the center of every massive galaxy, including our own. But not every supermassive black hole powers a quasar. The one at the center of the Milky Way is not active, or else we wouldn't live. But in some massive galaxies, their supermassive black holes are surrounded by gas falling inward. The gas forms a glowing accretion disk, and it can also launch powerful jets of material out into space. In a black hole, gravity is so strong that even light can't escape. And you may wonder the seeming paradox of black holes appearing bright. The black hole itself emits no light. It's a swirling gas and the energetic environment around it that makes quasars shine so brightly. In this diagram, there is a central black hole, and it has an accretion disk and relativistic jet. For a quasar, the energy originates from accretion onto a supermassive black hole. A supermassive black hole is a very dense source. So there is intense gravitational field. This is a millions to billion solar mass object and is confined to a region of less than a light hour across. And then the infalling gas around the black hole, the infalling gas forms an accretion disk around the black hole, and this accretion disk has the size of a few light days. And as the gas spirals inward, friction heats it to extremely high temperature, and then some of the gas is driven out into jets focused by magnetic fields. So that shows you the structure of the quasar phenomenon. And now that we've met quasars, let's zoom out and see what they tell us about galaxies. Quasars are more than just bright objects. They are cosmic tools. They light up their host galaxies and the material in the space around them. And that reveals gas and dust that are otherwise hidden. Quasars allow astronomers to observe the invisible parts of galaxies and the universe. And they help us study how galaxies and the universe evolve over time. When we look at the light from a quasar sorted by wavelengths, we see patterns, and we call this pattern a spectrum. It tells us what the quasar and the gas between us and the quasar are made of. In a quasar spectrum, emission and absorption features encode physical information. That includes the chemical elements present, the motion of gas and supermassive black hole properties, how fast the universe is expanding, and the cosmic web, which is the large-scale distribution of gas in the universe. So from quasar spectra, we can learn a remarkable number of things. We learn chemical composition from the line streams, which helps us understand the chemical evolution of galaxies over cosmic time. We learn gas motion and supermassive black hole properties as the width and the shift of the emission lines reveal how fast the emitting gas is moving, and from that we can estimate the mass of the black hole. And we learn redshift and cosmic expansion. It's by measuring how much the emission lines are shifted to longer wavelengths, or so-called redshifted, and we can then determine how far away a quasar is and how fast the universe is expanding. And we learned the cosmic web, and it's illustrated by this absorption line spectrum of a quasar. The gas clouds in the intergalactic space, they're often too diffuse and too dim to be observed directly in emission, but we can study them in absorption. We can analyze the hydrogen and the metal absorption lines. They come from the intervening gas along our line of sight to the quasar. And then we can map the large-scale distribution of gas in the universe, and we can track also how the intervening galaxies acquire the fuel they need to form stars. So think of quasars as cosmic flashlights. They illuminate parts of the universe that we otherwise couldn't study. Galaxies change a lot over billions of years, and quasars mark an especially active and energetic phase in a galaxy's life. During this phase, powerful outflows from quasars can blow away the gas needed for a star formation. This can quench the galaxy, which means ending its star-forming phase and transitioning it to a more passive phase. And this is an artist's concept. Cold gas from a halo of much larger scale than the galaxy is flowing into and out of this galaxy. And because cold gas is the raw material for star formation, these large-scale gas flows are feeding and feedback processes for the galaxy, and they may shape the galaxy's evolution. And I put a star symbol at the center. This just indicates the presence of a quasar, and there are two light beams emanating from it. The word quasar stands for quasi-stellar object. Quasar is quasi-stellar object. Quasar-driven outflows can regulate star formation and accretion onto supermassive black hole. And the impact of a quasar on a massive galaxy can be that cold gas is removed or heated up, is removed from the galaxy or is heated up so that it can no longer form stars efficiently. And then the galaxy is said to be quenched. So studying quasars helps us understand galaxy evolution. Normally, quasars are visibly luminous, but some quasars are shrouded by thick clouds of dust. Reddened quasars are a special class of quasars that appear unusually red, and it's because the blue light is blocked. The dust blocks the shorter or the bluer wavelengths and makes them appear red, and it's like how sunset appears red. And I have a schematic diagram, and this is showing the evolution sequence in some popular theoretical models. It's like a life cycle. The left picture, this is like the youth stage of a galaxy. The central black holes initially grow in obscurity. Some triggering events for starbursts, perhaps mergers of two smaller galaxies, shroud the galaxies in gas and dust. And then the middle picture is like the teenage growth spurt stage of a galaxy. So the central black hole continues to grow until it's massive enough to power a quasar. And then important quasar-driven outflows is expected to happen during this brief dusty blowout phase. During this blowout phase, outflows remove gas and dust from the galaxy. And then the right picture shows the maturity stage of a galaxy. And the blowout reveals the visibly luminous quasar and drives the transition to this later quiescent galaxy phase. If you can see colors well, the middle image is not exactly red, but it's redder than the right image. So we say the quasar is reddened. So the popular theories are that dusty starburst, possibly triggered by mergers, evolves into a reddened quasar driving blowouts, evolves into a visibly luminous quasar in a galaxy undergoing quenching. And since reddened quasars may represent a short-lived but powerful phase, they are excellent laboratories for testing these popular theories on supermassive black hole and galaxy evolution. And they're important for studying rapid black hole growth and the early stages of galaxy evolution. So how do we study something so far away? Yes, that's me. Modern tools let us see quasars in extraordinary detail. On the ground, with adaptive optics, we correct for the blurring caused by the Earth's atmosphere. Turbulence of the atmosphere distorts images. It causes blurring at even the best sites on the ground. And it's what causes stars to twinkle. It's the same effect. Adaptive optics works by measuring the distortion, and it rapidly compensates for it using deformable mirrors. And then with so-called integral field spectroscopy, we can get a three-dimensional data cube for any observing target, 2 spatial dimensions and 1 wavelength dimension. And we get a spectrum at every pixel in an image. Another name for integral field spectroscopy is hyperspectral imaging. And we can map the structure, the motion, and the chemistry of the dust enshrouded regions of quasar host galaxies. Adaptive optics and integral field spectroscopy are available at Keck Observatory on Mauna Kea in Hawaii. These technologies on large telescopes help us map the gas flows and dust around quasars. We use these observations to assess the impacts of visibly luminous quasars as well as reddened quasars. We want to assess their impact on their host galaxy star formation. And it's not necessary to go on a trip to use the Keck telescope. We just remotely connect from here in Southern California to the computers and the crew on the summit on Mauna Kea. In fact, I've only been to the summit once in my entire career, and I went there just to see how it looks like after I have used it so many times. And I took a selfie with the primary mirror of a Keck telescope. You can see it has a honeycomb structure and is 10 meters in diameter. In space, we have another important observing facility, James Webb. It's a new eye for us to observe quasars that are otherwise hidden behind gas and dust. The Webb is a feat of engineering. It has a 6.5 meters mirror of also a honeycomb structure. It's put in a cold and sun-shielded orbit. is 1.5 million kilometers away from Earth, is much farther away than the Moon. And it's not just a NASA project, but it's an international collaboration of thousands of scientists and engineers. Visible light is just a narrow slice of the electromagnetic spectrum. The full electromagnetic spectrum, from the shortest to the longest wavelengths, spans from gamma rays to radio waves. Why study infrared light? Infrared light can travel through thick smoke, dust, fog, and some materials. And that's why firefighters and astronomers, we all build infrared cameras. So the web can peer through and examine dust. The same astronomical object looks very different in visible light versus in near-infrared light versus in mid-infrared light. And why launch telescopes to space? Because the atmosphere absorbs UV, X-ray, and most of the infrared spectrum, we have to move some telescopes above the atmosphere. The Webb is sensitive to specifically the 600 nanometers to 28,000 nanometers range of the electromagnetic spectrum. And so it bridges the Hubble's long wavelength limit and the Spitzer Space Telescope's short wavelength end. Now I'm going to introduce the research findings by me and my collaborators. I put down some journal publication references. In case you're interested, you can skim through those papers or at least the paper abstracts and figures. And you can also just look at my name and go to my website. I have a homepage and you can find things about my research. I study reddened quasars and how they differ from normal quasars that are visibly luminous and unreddened. I also study the halo gas surrounding and falling toward quasar hosts, whether the quasars are reddened or unreddened. And why is our research important? Our findings on reddened quasars both inform and challenge our current understanding of galaxy evolution. And the interplay between gas inflows and outflows is a key part of how galaxies and their central black holes roll together. Quasars in general drive gaseous outflows. Compared to normal quasars, reddened quasars drive more energetic outflows. We've observed some of the fastest winds ever recorded, with gas flying out at thousands of kilometers per second in a relatively small region. And I want to show some actual spectral data we took, and I will guide you through it in reading them. This is the ionized oxygen emission line spectrum of a reddened quasar. We like to study oxygen because it's an abundant element in the universe. The strength of an emission line is measured relative to the continuum light which comes from the accretion disk. And so we normalize the observed flux to the continuum level, and a value of greater than 1 in the normalized flux means there is line emission. And we plot normalized flux not against observed wavelength, but relative velocity. We translate the observed wavelengths to a velocity scale in the frame of the galaxy by using Doppler shift formulas. And think about it. The light-emitting gas has to be in the foreground of the quasar, or else its light will be obscured from our line of sight. So the light-emitting gas is in the foreground of the quasar. If the light emission happens at a wavelength shorter than expected in the quasar's frame, the emission is blue shifted relative to the quasar. and the emitting gas has to be flowing toward our direction and away from the quasar. And our sign convention is that negative velocities are blue shifted and positive velocities are red shifted. It's just a sign convention. So spectral lines at negative velocities trace gas outflows. I said quote-unquote line, but this line is very Doppler broadened. These lines are very Doppler broadened, so that's why they don't quite look like lines. They're Doppler broadened. And so for a comparison, I overplot a normal quasar spectrum. You can actually see the lines. So compared to normal quasars, reddened quasars have unusually strong and blue-shifted and broadened emission lines from ionized oxygen. These lines trace energetic gas outflows. And so from the spectra of the reddened quasars, we can reveal gas blasting out at thousands of kilometers per second. The quasar winds result in very kinematically disturbed gas in the galaxy. And we've measured these outflows have the energetics required by theoretical models for suppressing excessive stellar mass growth. The energetics are sufficient for suppressing excessive stellar mass growth. So the outflows provide efficient negative feedback on the galaxy's growth. We also found that outflows in reddened quasar galaxies happen in a smaller region compared to normal quasars. And so the outflows are young and they're still expanding outward. Eventually, quasar winds can regulate and even quench star formation. But at the evolution stage of being reddened quasar, the outflows have not yet reached the entire galaxy, still expanding from the center. So it's like young storms still brewing in the galaxy cores. And this gives support to the standard theoretical model of the evolution sequence. Reddened quasar, the dusty blowout phase, is in an earlier stage than visibly luminous quasar. Quasars, whether reddened or unreddened, they have giant halos of hydrogen gas extending far beyond their host galaxies. We study hydrogen because it's the most abundant element in the universe. The halos extend to tens to 100 times the galaxy's size. An example is shown in an image. This is a very long exposure image to detect the faint glow of the hydrogen halo. I've observed definitive signs that some quasar host galaxies are pulling gas inward from their surrounding halos. And that gives support to some popular theories in which gas inflows fuel the star formation and grow the central black hole. And I want to show some more spectral data I took. This is the neutral absorption line spectrum of a normal quasar. The neutral hydrogen halo gas in front of the quasar host galaxy absorbs light. Absorption is measured relative to the unabsorbed level of the quasar's light, so we normalize the observed flux to that. A value of 1 in normalized flux would be no absorption, and then 0 would be no residual flux after very strong absorption. And again, we plot normalized flux against relative velocity. We translate the wavelengths in observer's frame to velocities relative to the rest frame of the galaxy. And the absorbing gas has to be in the foreground of the galaxy, otherwise it wouldn't be absorbing the galaxy's light. And so if absorption happens at a shorter wavelength than expected, the absorption is relatively blue shifted, And the absorbing gas has to be flowing toward our direction and away from the galaxy. And if absorption happens at a wavelength longer than expected, then the absorption is relatively redshifted, and it has to be flowing away from us and toward the galaxy's direction. Again, our sign convention is that negative velocities trace gassing outflows, and negative velocities are blue shifted and positive velocities are red shifted. And so absorption at negative velocities trace gassing outflows, and absorption at positive velocities trace gassing inflows. Real data is going to be messy, and not all the absorption comes from the halo gas surrounding the quasar. And some actually originates from unrelated intervening gas that just happens to be along our line of sight to the quasar. So on top of the data spectrum, I also plot these smoother curves, and they're just showing our modeling of just the physically related halo gas absorption. And anything else, this is unrelated absorption. Stepping back, why do we invest in this research? Why does it matter? Quasar research is connected to the big picture cosmic questions. To understand how galaxies get their gas and fuel star formation, to understand how supermassive black holes and galaxies interact over cosmic time, and therefore how the supermassive black holes affect galaxy evolution. To explore what the early universe looked like when the galaxies were young. Because quasars are so bright, we can see them even when they're billions of light years away. And that makes them powerful probes of the distant past of cosmic history. And this cartoon shown here is using a quasar as a background light source. And this is to study the intervening gas along the line of sight from the telescope to the quasar. Because the universe is expanding, galaxies and gas clouds further away from us recede faster, and the light is more highly redshifted. And as the light from the quasar reaches the farthest cloud, a light is absorbed, which will be stretched to some reddish wavelength by the time it reaches us. So that's shown in picture A. And then as the light from the quasar reaches the middle cloud, again, a light is absorbed, and this light is stretched to some yellowish wavelength by the time it reaches us, and that's shown in picture B. And then as the light from the quasar reaches the closest cloud, another light is absorbed, and it will be stretched to only some bluish wavelength by the time it reaches us, and that's shown in picture C. So the total spectrum we observe at the telescope looks like picture D. Large ground-based telescopes like Keck and space telescopes like James Webb are providing us unprecedentedly detailed views of quasar environments. These existing observatories continue to improve our understanding of the universe, and the next generation telescopes will push our understanding even further. So I've been mostly talking about observations. Some researchers also run computer simulations of the universe, and these figures are actually results from simulations. Astronomers simulate the cosmic web based on some theoretical models, and then they simulate the corresponding absorption line spectrum of a quasar that is observed behind a part of the cosmic web. As we gather more observational data, we refine our theoretical models, we test new ideas, and we also uncover new surprises. We are just beginning to answer the big questions. Maybe one day astronomy enthusiasts like you will join this exciting quest. You could be part of the discoveries. This is not just abstract science. It's something we all can be a part of. You don't need a PhD to join this adventure. And here are some accessible entry points for our students or any community members to participate in astronomy. Of course, you can take astronomy classes here and also at nearby colleges. You can visit a planetarium and attend public events like this one here, or watch planetarium shows. You can join public observing nights, which is what follows after my talk. You can also contribute to citizen science projects. For example, there's the Galaxy Zoo. You can look at what's Galaxy Zoo. It's a project where you help scientists classify galaxies based on their shapes. And some galaxies in their database may be active galaxies. You can look into research internships and outreach programs. You can look for these opportunities at observatories and universities near you. I personally come from a humble background, and I know sometimes it can feel hard to imagine yourself doing this kind of work, but I want all of you to feel encouraged. To wrap up, quasars are like cosmic lighthouses. They are powerful, they are bright, and they're full of information. They illuminate, literally, our understanding of supermassive black holes, the life cycle of galaxies, and the universe's history. Every new discovery raises new questions, and this is what makes science exciting. Thank you for your curiosity, and I'll be happy to take questions. Yes, please.
About how many galaxies are known to us?
The question is about how many galaxies are known to us. Let me count how many zeros. 8 plus 3, that's 10 to the 11 galaxies. I think that's the rough order of magnitude. I think it's about 10 to the 11 galaxies. So what's the significance of this number? So actually, when you count galaxies, galaxies come in different masses and different luminosities. And of course, when the galaxies are too faint, too far away, you cannot observe them, but we still can run models, and we can try to predict the evolution of galaxies, evolution of the universe, and then we can still make some extrapolations to how many galaxies there are in the very distant universe. And so I think now the order of magnitude estimates we have is 10 to the 11 galaxies. Yes?
What's the time scale between the phases of the quasar? Like how long does it take to go from adolescence to planetary reach? How long? What's the time scale?
Oh, sorry, I forgot to repeat that question. Yeah. The first question was how many galaxies there are in the universe. And this question from this gentleman is, what's the time scale? And let me go back to the picture showing what we believe is the evolution sequence. And the question is, what's the time scale from like a dusty starburst stage to the reddened quasar stage to the luminous quasar stage, and then maybe the later more mature galaxy stage? What's the time scale of the different stages? So the lifetime of a galaxy is on the order of billions of years, and the lifetime of a quasar is only on the order of 1,000,000 to 100,000,000 years. So a quasar is a short-lived phase in a galaxy's lifetime. About 1% of a massive galaxy's lifetime would be lit up as a quasar. And then the reddened quasar phase is even more short-lived. The reddened quasar phase is an even more short-lived phase compared to the full quasar life cycle. Is maybe about, I think, if we just count how many quasars are red and how many are not red, maybe 10 to 50%. So reddened quasar is an even more short-lived phase than the entire quasar phase. And the quasar phase is a short-lived phase compared to the entire galaxy's lifetime. So even though it's so short-lived, but it's powerful, and so it still has profound effects on a galaxy's evolution, and that's why we study them. Thank you. I think I see this hand first. Hi.
Do quasars affect one type of galaxy more than another type of galaxy? Like would they affect irregular galaxies more than they would spirals or peculiar galaxies? Or does it really make a difference?
So the question is, does quasar affect one type of galaxy more than another? Like I've shown pictures of elliptical, spiral, irregular galaxies. Do quasars affect one type of galaxy more than another? So first of all, you need a massive galaxy to have a supermassive black hole, and you need a supermassive black hole to be able to power a quasar, to have enough energy to power a quasar. And so now the evolution picture we believe is that initially, perhaps the galaxies will start out a little bit more irregular but disky, and then when you have a powerful quasar, it's going to affect the galaxy's evolution, and it can turn a disky galaxy like these into the shape of an elliptical galaxy. And so part of the quasar's effect is also to transform the shape of a galaxy. And so in elliptical galaxies like these, we don't often observe a powerful quasar still on. It's probably after the quasar has been turned off.
Yeah, because maybe they're too old.
Yeah, the question is whether these are too old. I would say they are mature. The galaxy is mature.
Well, that's another way of saying it.
Yeah.
Question because most of the universe is made up of elliptical galaxies.
So the question is, most of the universe is made up of elliptical galaxies. I guess so this is just a schematic of showing different shapes. I guess when I was saying elliptical galaxy, I was thinking about the giant elliptical galaxies, not the small spherical ones, and they have different evolution pathways. Yeah. So I guess in short, do quasars affect one type of galaxy more than the other? They affect massive galaxies, and you need a quasar so that the massive galaxies don't overgrow, because we can observe how massive galaxies are in the early universe and how massive they are at present time. Without a quasar to blow away all the gas and dust and quench star formation, the galaxies will become overmassive, and then our picture would not be consistent. Yes?
So I've just kind of become fixated on this notion that maybe our whole universe is on the inverted side of a supermassive black hole. And of course, it's like what we see is our observable universe, and what's kind of on the other side of that is not observable by definition. But so I've been kind of trying to figure out how this notion might gain evidence for it. And so I was definitely interested in the question by the gentleman over here, how long that quenching process takes. And I was wondering if there's any relation between that period of quenching versus, say, like kind of the post-Big Bang period of how long it takes to reach cosmic, at the end of cosmic inflation, or more stable kind of period of cosmic inflation. If there's any relationship there. And then just more generally curious if there's any thing that you've come across in your research or your own conclusions that might put this idea of us living on the inverted side of a black hole to rest, where you would say, oh, that's just not even possible?
So let me try to repeat the question and the information. So first is the idea about the notion that we may be living on the inside of a supermassive black hole, and that's what our observable universe is, and we don't see things beyond. So I think the idea that we live on the inside of a supermassive black hole, I think I've seen it in science news. I think that's like a relatively recent idea, and that's not exactly directly connected to my research. But the notion of an observable universe, that has been a much older idea. And that idea is a lot more simpler. It's just saying that because light has a finite travel time, light travels at 3 times 10 to the 8 meters per second. And so that sets the boundary of how far away you can observe. And beyond that, we have no means of communicating with those parts of the universe, and that defines the size of the observable universe. And I think the idea of we live on the inside of a supermassive black hole, I think this is a relatively more new and maybe not too popular idea, but I can definitely look up into that and give you a better answer. If you can send me an email, look up my name, I can give you a better answer on that. But I don't think that's a popular idea. And then your other questions, that's about the time scale of the different phases of cosmic history. So you mentioned perhaps the cosmic inflation stage, and then the quantum time scale. What are the different time scales of the different stages of the universe? So the inflationary epoch of the universe's history, that's a very short-lived period after the Big Bang. That's much less than 1 second. And then it takes millions of years after the Big Bang for us to have the first galaxies. So even though I was saying early universe is not like early as in right after the Big Bang, it still takes millions of years for the first galaxies to appear. But I still say this is early because the entire universe's age is 13.7 billion years. And so I say early universe, but this is quite far away from the inflationary epoch. Yes?
I understand that quasars are extremely rare, as in, like, they're the closest one is 1 billion light years away from us. That's correct, right? The closest one is really far away.
So your question is quasars are very far away.
Like, the closest one is like 1 billion light years away, right?
Yeah, so let me repeat the question. What's the closest quasar and how far away are quasars typically? Actually, the 2 quasars I showed are among the closest. So this one is the closest ever discovered. This is less than 1 billion light year, and that's why you can still see the galaxy structure. And this one, I think, is still one of the closest, but this is like 2 billion light years away, so you already don't see much of the galaxy structure, and you need even more exquisite spatial resolution to see the structure of the galaxy. So yes, quasars are very far away, billions of light years away, yes. Yes?
Do supermassive black holes always produce quasars?
The question is, do supermassive black holes always produce a quasar? No, so every massive galaxy has a supermassive black hole at the center, but not every supermassive black hole powers a quasar. You need an enormous amount of gas to be fed into the central black hole to have so much energy and so much friction to heat up and make the gas glow and to have a quasar. So for example, our Milky Way has a central supermassive black hole, but it's not a quasar. Otherwise, it's going to be so bright we wouldn't be able to live.
Yeah,
Yes.
I was just looking at the black hole right there. So you have the black hole, you have the gases going inside of it, and then these gassy lines going out. That's the light from the quasar. Is that right?
So the question is about this schematic diagram here. So this beautiful picture is prepared by Jessica, but this is an accurate picture, accurate artist's impression of what we think is going on in a quasar. So this is like an accretion disk. And so this is gas spiraling in, and then at the center, gravity is so strong that even light cannot escape. And then what is this jet? So you have this jet because of magnetic field, and so this accretion disk is plasma, so there is conducting material, and so that generates magnetic field. And then because of some complicated physics, you actually need to run computer simulations for that. You can derive the results that you will generate magnetic field lines so that they will focus and collimate these jets going out. And these jets is made of relativistic particles of electrons, positrons, some protons, and some heavy atomic nuclei. But mostly is electrons, positrons, and protons. That side. Maybe I walk this way.
You can answer the person up there front first.
Yes.
Well, I was just wondering, since you're pointing at that quasar, how do you name quasars?
The question is, how do we name quasars? You know, for objects that are visible with naked eyes, usually we give them a name because those are like more ancient and they're named by ancient humans. But quasars are not visible to naked eyes, even though I say they are very luminous, but because they are so far away, we don't see them with naked eyes, so we don't give them interesting names, and they only have catalog IDs. This one is called 3C273, and this one is called MRK231. We give them IDs in catalogs. Yes. Yeah, the question is, we can't really see them with naked eyes, but we need telescopes. Yes, yes. Even though this is like the brightest quasar, and this is like the closest quasar, but we still need telescopes to see them. That's why they weren't discovered until the 1960s, when we have powerful enough telescopes to see them. Mm-hmm. Yeah, so the question is, sorry, are you saying more? Yeah. Yeah, so the question is, what do we learn about the mass of the black hole from the quasar? And this is really just a Doppler shift thing. I want to show a spectrum. So like this. This is supposed to be a line. A spectral line is supposed to be narrow, but it's so Doppler broadened. Its velocity width is like thousands of kilometers per second. So this is a very energetic thing. So this part is actually gas flowing out. But some of that is not gas flowing out. Some of that Doppler broadening is just from gas circling around the quasar. And so when the gas is circling around the quasar, the emission line you observe is also going to be broadened. And it's from this line broadening, and you can measure how much kinetic energy there is. And from this amount of kinetic energy, that gives you an idea of how much gravitational potential energy there is from the black hole. And from that, you get the mass of the black hole. Yes?
Quasars uniformly bright in all directions, and if they're not, it's dependent on which way it's facing. And then the correlated to that is if it's facing not towards us, does it mean we can't see it? Potentially there are more quasars than we think there are.
So the question is, are quasars uniformly bright in all directions? And if there are not, does that mean there are some quasars that we couldn't see, and there are more quasars than what we just count the numbers? So I really like that question. So if you just look at this structure, if your eye is here, if your telescope is here, you see the bright accretion disk. And because this structure is not like a uniform sphere, if you look at it in other directions, so actually on larger scale than this accretion disk, there is actually also a dusty torus around the accretion disk that's not shown in this schematic diagram. So if you look through a very thick dusty torus, that's going to block out all the light and you cannot see. So it's true that in some directions you would not see a quasar. So we need to do modeling of the geometry of the quasar, and then we need to extrapolate how many quasars there are. Yes.
Is it theorized that all galaxies go through periods of activity if they're fast enough? Not as in a quasar, but like a less active, active galactic.
So the question is, do all galaxies go through an active galactic nuclei phase or any active and then quiescent phase? So the word quasar is related to what you said, an active galactic nucleus. A quasar is like a very bright active galactic nucleus. And so some galaxies, they don't power something as bright as a quasar, but they still power an active galactic nucleus. And in general, and the physics, the basic physics for a quasar and an active galactic nucleus is basically the same. It's just that quasars are the brightest among them, most powerful among them. And in general, in the early universe, when the galaxies, when it's in the early distant universe, the galaxies were more actively forming stars. And then in the more local universe, some galaxies have stopped forming stars while some is still actively forming stars. So as the universe ages, it's true that galaxies' activities are also coming down. The star forming activities are coming down. Yes. So the question is, if the black hole goes dormant, is there a way for them to turn back on, or they just stay dead like this? So there are short-lived events called tidal disruption events. If you've heard of this name, so if you manage to find a large amount of gas to feed into an inactive supermassive black hole, it can light up again. So for example, if a star happens to plunge into a black hole, if it's so unfortunate its orbit, it happens that its orbit is that it plunges into a black hole, a star is dense, it's a dense blob of gas. So that's a lot of gas and that can light up a black hole. But for our Milky Way center, there is not enough gas to light up the black hole again. But you can have other ways to feed a lot of gas to an otherwise already dormant supermassive black hole. For example, like in this picture, if it merges with another galaxy, that's going to give it a lot of gas, and that can light up a black hole, and that's why it will become a quasar. And you can have this merging process again. Yes.
Just wondering how you envision AI kind of changing or facilitating your field of research, and also wondering separately if government funding, I assume, is the primary source of funding for space like that. So, like, are there other alternatives, private or otherwise, that you envision that could step in at that risk?
Yeah. So. The first question is, how is AI is changing or helping the landscape of research? And so, for example, I mentioned there is this Galaxy Zoo project. It used to be that we use only volunteers to visually help us classify galaxy. So basically, if you're interested, it will show you a picture and ask you, do you see spiral arms? Yes or no? How many spiral arms? And of course, this kind of work, now you can use AI to do some of that. So now we are becoming a bit less reliant on citizen science efforts, so we can use AI to do a lot of that work. But I personally think that sometimes humans can still see features that AIs cannot see. And so they are complementary, but I don't think AIs can completely replace that kind of effort. But it's true that a lot of the more mundane work can be done by AI now. And then the second question is about the government funding situation, and can other sources of funding supplement the budget crisis going on in basic science now. It's true that the majority of funding in science, it comes from federal government, but not 100%. So for example, I showed this Keck Observatory. Keck is its own funding foundation, so it's not entirely from the government. But Space Telescope, this is funded by NASA, so yes, it's 100% from the government. So I don't think now we have found a solution, but what I've seen, what my collaborators and colleagues are doing is that some people, for example, they have transitioned to a higher teaching load because research funding is drying up and they still do research as a hobby. And some people have moved on to maybe data science jobs. They have more money in those fields and they also do research as a hobby. So I don't think we have a solution to the funding situation, but the research is still ongoing. Because nowadays we have a lot more data than manpower or woman power. I think you don't always need direct connection to a telescope to do astronomy research. There is so much data out there waiting for people to analyze. So as long as you can contribute your free time, you can do an astronomy project. There first, yeah.
Oh, Agnes. What are we looking at tonight through the telescope?
The question is, what are we looking at tonight outside using the telescopes outside? I think it's run by Jerome Fang, it's not run by me. But tonight is going to be cloudy. I think usually when the weather is cloudy, we let people see the moon, but the moon is not up tonight. So I don't know if we can actually see anything tonight. But if there is a hole between the clouds, we can see what we find. Yes?
You said a couple of times about if there were quasar in the middle of a Milky Way galaxy, you wouldn't be able to live. What is that? Tell me more. Tell us more about that.
Yeah, so I was saying, the question is, I've said a couple of times, if there were a quasar in the center of the Milky Way, we wouldn't live. What do I mean by that? Because a quasar shines very brightly, and it's not just bright, but it's harmful gamma rays and UV and X-ray photons, and so that's not good for life. Yeah. If it's at the center of the Milky Way, that's not too far. Yeah. Thank you. Yes. I think at the back first.
How dense are quasar stars?
The question is, how dense are quasar stars or quasars? So you can use, I don't have a calculator in my brain, but you can, if you have a calculator, you can do this calculation. Where do I have a diagram? Here. So if this is 1 billion solar masses, and if this region is of the size of less than a light hour is a distance measure, is how far light can travel in an hour. So if you just do that simple calculation of mass divided by volume, you can get a density for this region. So 10 to the 9 times the mass of the sun divided by a volume of a size that's about a light hour across. Yes?
You know, I can scout a little louder. I was wondering, is that diagram the magnetic field spiral, and I keep thinking about like, why would it be spiraling? And also, I'm assuming the top part there is the outflow or the inflow.
The question is, why are the magnetic field lines spiraling, and is that outflow or inflow? So the magnetic field lines, they are generated by electric currents, and you will need some complicated magneto-hydrodynamic simulations to actually get the actual shape of the magnetic fields. But you know, whenever you have an electric current that generates magnetic field, and this is a plasma, that there is conducting material, and it happens so that they just twist the magnetic field lines this way. Otherwise, you wouldn't be able to collimate the particles to go out like this. And this is an outflow. This is a jet. This is relativistic speed. This is like 90% times the speed of light going out. Yes. The question is, what will happen if two black holes end up merging? They become a bigger black hole. It's like this. You have a black hole at the center, another black hole at the center. They merge. There is a more massive black hole at the center. Yep, they can merge, and sometimes you can have three of them. They can also merge. Yep, they just become a bigger black hole. And when you bring in all the gas around them, the black hole can light up as a quasar. Since there is one more question, yes.
Right, so 2 dusty star bursts equal a reddened quasar.
The question is, 2 dusty starbursts equals a reddened quasar. So that's a picture we believe is happening. So that also depends on exactly the composition of the gas. It also depends on what type of gas we have inside. So not all dusty starbursts merge and then it will become a reddened quasar. If the gas inside is not the kind of gas that will be favorable for lighting up a quasar, then this doesn't happen. And also, so this is like a popular theory, and there are other alternative models challenging this theory. And some theorists will tell you that you don't need mergers of 2 smaller galaxies. Even a standalone galaxy, maybe there is some gravitational instability inside it, and it can also collapse inside it and form a quasar. But this is the picture that's more popular. Yes. So the question is, I think the first one is a more personal one, how I got into astronomy and how I just remain passionate about this field. So when I was small, I watched NASA documentaries. They were freely available and on TV, and then I went to stargazing camp. So that was like when I was small, and that camp was part of an English class, and for some reason they inserted a stargazing camp, and that got me interested, and I just stayed interested. And I think perseverance is important because you don't earn that much being an astronomer. So you need perseverance to stay in the field. You need passion, you need perseverance. And then I think another question is, with all these next generation telescopes and AI and with all the new things happening, what will be the breakthrough I think is going to happen in astronomy? So I've been mentioning that this quasar research is connected to the bigger picture of galaxy evolution. I think actually the entire field of galaxy evolution, I am hopeful that the big questions can be answered in maybe 20 years. I think by then galaxy evolution would be like considered a mature field, and then we would have, but then there will still be some more fundamental questions about cosmology. I think we are going to move on from what we are currently doing about galaxy evolution to more fundamental questions about cosmology. And then another breakthrough is going to be on much smaller scale, that's finding habitable planets. So I think it will be too much to say we are going to find aliens. We don't know. But I think what's really on the horizon, what's reachable, is we can find other planets that could look like they're habitable to life. And that would bring us back to questions about origins of life on Earth and in the solar system. I think that's another area of where breakthroughs can happen. Yes?
What are the big questions that are answered in the field of galaxy evolution?
The question is, what are the big questions that are being answered?
That you're wanting to be answered too.
That I want to be answered. Yeah. Okay. Yeah, thank you. The question is, what are the big questions that I want to be answered in the field of galaxy evolution? You know, so now with the launch of James Webb Space Telescopes, we can really see to the very distant past, and we can see out to the very early universe, and we are trying to find out when did the first galaxies form. And we are just pushing onto that record. Like maybe a year ago, people were saying the farthest galaxy is maybe at redshift 7, like the light is being stretched by 7 times compared to what's in its rest frame. The light is being stretched by 7 times, that's redshift 7. And now there are some people claiming they find galaxies at redshift 25, so that's even further away. So when did the first galaxies form? I want to answer that question. I think when you push to further and further away, you won't find galaxies indefinitely. At some point, the universe, in the very early universe, the universe will be dark. So I think I want to answer the question of when did the first galaxies form? Seems there are 2 more questions. Yes. Yes, hi. So the question is about when I talk about the galaxies pulling in gas, inflowing gas from the halo and then blowing out, is that only in the jets or in all directions? So there are outflows and inflows going on in different scales. These pictures are a very different scale. So like for this picture, this is like at the very center, very close to the black hole. But and then, for example, this artist's impression here, we are showing scales of like 1,000 light years. And then this picture is like a very zoom in of the very center region here. And so I think on the larger scale, things are going to be mixed up and messy, and you don't always see like 2 jets coming out so cleanly in just 2 directions, but the outflows and inflows are going to happen in all directions on the larger scale, it's going to be messy. But if you talk about the scale very close to a black hole, like this schematic diagram here is at the very center, then yes, we're going to see there's a jet. The outflow is collimated in a jet.